Hello, welcome to Introduction to Continuity and Momentum Conservation Equations. I'm Hugo Castillo Sanchez, and the goal of this presentation is to give a brief introduction to the most used equations in CFD, which is firstly the mass conservation or the continuity equation, and then a momentum conservation equation. So this presentation is going to be split into the first one, which is this one. I will be talking about the mass conservation equation, how it is derived, what are the origins of this equation, what is its physical meaning, and then in the next video I will be focused on talking about the Newton's second law for fluids, and then which is used to obtain the momentum conservation equation, which is also used to obtain the Navier-Stokes equations. But yeah, let's start. If you watch my previous videos, or if this is the first time that you are watching my videos, I describe the equations that are commonly used to simulate the flow of a fluid. So we actually have a couple system of partial differential equations. The first one is a continuity equation, which is just the mass conservation, which tells us that the mass that enters volume control is the mass that exits the volume control. And then on the second, here in this second block, we have the momentum conservation equation, which is just basically Newton's second law. So we have an acceleration that experiences the fluid has to be equal to the forces that act on the fluid. So we have a temporal acceleration, we have a spatial acceleration. This is the density of the fluid, and then the forces that are acting over the fluid it can be the pressure gradient, which is the effect of a pump. We have the internal forces, and then we have a source term, which can be, for instance, the effect of gravitational effects or electromagnetic effects, external electromagnetic effects. And then we might need additional equations to, depending on the problem. So for instance, if we are interested in simulating a polymer, chocolate, volcanic lava, air, so we might need, we need actually a constitutive equation, an equation that relates the stresses, the forces that are applied over the fluid, which can cause deformations over the material fluid, over the fluid material. So we need to specify this equation here. It is different for every fluid in the world. And then if we are solving non-isothermic flow, that means that there are changes in temperature. We also need an energy equation. And then if we are simulating a gas, we need an equation of a state that relates pressure with volume and temperature. These equations are mostly used for gases, so I will be focused mostly on liquids, so we will not be interested by now on this equation. So let's start with the first equation, the mass conservation equation. So let's assume that we have a volume control, and over this volume, a mass of fluid can enter the volume, but it can also exit. So this volume is fixed. We also have a differential surface over here. If we sum, that means that we can, for this whole surface, we can obtain small pieces of surface, and if we sum all this differential of surface, we will get the total surface of the volume control. And then we also have a unit normal vector which points in this direction for this case. So I also want to calculate some quantities, some important quantities that we will be used to derive the continuity equation. So the mass flow can be calculated as follows. So the fluid that is entering here has a density which has units of kilogram over cubic meters. And then if we multiply the density by the velocity of the fluid, because the fluid is moving with a velocity u is a vector, the bold letters are vector quantities, and then if we multiply this quantity by the unit normal vector, we get the following dimensions. So as I said before, the density has these units, the velocity normally has units of meter over seconds, or it can be feet over seconds, depending on the unit system that you are using. And then the normal vector doesn't have units, but the differential surface has units of area, which is square meters. And if you multiply these units, you will get kilogram per second. So this quantity tells us the flow of mass that is crossing this volume control. And then the volumetric flow, which has units of cubic meters per second per units of time, can be calculated as follows. We don't multiply by density, so actually this product without the density just gives us the volumetric flow. And then we also define a new quantity, which is the mass flux. You can see that the mass flux is defined as the density multiplied by only the velocity, and this gives units of kilogram over square meters multiplied by second. So mass flux is just the flow of mass that crosses a surface. That's why we have units of kilogram per meter square per second. So these quantities are used in engineering to estimate flows, volumetric flows. So I'm just introducing the concept here because we will use it a lot, and in CFD we also use a lot of these concepts. And then the total mass. So the density, if we multiply the density and we integrate it over the volume, so that means we sum, we estimate the volume integral of the density in this volume control, we will get the total mass of the fluid. And then we can also obtain the derivative with respect time of the total mass. So I will explain this concept in a second. What is accumulation? So a mass balance, a simple mass balance without chemical reaction can be obtained as follows. So the accumulation has to be equal to the integral, the surface integral of this quantity, which we saw was the mass flow. So what is the meaning, the physical meaning of this equation? So this equation is telling us that the mass that enters the volume control, the mass of fluid that enters here, has to be equal to the mass that exits the volume control. How do we know if the fluid is entering or leaving the volume control? That information will be obtained from the unit normal vector. You will see an example of this in a second. And as I said before, this gives us units of mass flow. And then if you sum this mass flow across all the surface of the volume control, you will get the total quantity of mass that is entering the volume control, and the mass of fluid that is leaving the volume control. So normally, in most of the cases, what enters, the quantity of fluid that enters volume control has to be equal to the quantity of mass that leaves the volume control. But if that doesn't happen, that means that some quantity of mass is being accumulated in the volume control. So that's why we introduce the accumulation term. So the mass balance, the general mass balance, tells us that the accumulation has to be equal to this quantity. So just to explain this in a clearer way, so let's assume we have a cylinder. So this cylinder has a phase 1, and yeah, this is the cylinder with phase 2. So some fluid element is entering through this inlet, which is the one that has phase 1, and then the unit normal vector is pointing in this direction. And then here in this phase 2, the fluid is leaving the volume control, this cylinder, which this velocity, but now then unit normal vector is pointing in this direction. So if we assume a steady state, that means that the accumulation term is going to be equal to 0. There is no mass being accumulated here. So all the mass of fluid that is entering through here, through the inlet, will be equal to the mass that is leaving here. So the fluid that is entering here will leave here. So there is no mass being accumulated here. So assuming this, the equation for the mass balance is reduced as follows. So let's calculate this integral over phase 1. So we will obtain the integral over this surface, surface 1. Then the density is not going to change. So we have density and then the velocity, this one, multiplied by this unit normal vector, multiplied by the differential of surface. And then how do we calculate this quantity? So if you remember your linear algebra or your basic mathematics lectures, calculus vector, the scalar product can be estimated as follows. We have an interior product, a vector product. So this vector product, the scalar product, can be expressed as follows. The magnitude of the vector u multiplied by the magnitude of the vector n1 multiplied by the cosine of theta. And theta is the angle between these two vectors. So we express this integral as using this relation as here, as it is shown here. And then this magnitude of the vectors are constant, so we put them outside of the integral, and then we only have the integral of the surface, which is S1, which will be the surface here, which is pi multiplied by the ratio square, pi multiplied by the ratio of this cylinder, of this circle, to the exponent 2, to the 2. And now we need to estimate this angle. So the angle between these two vectors is actually 180 degrees, because they are pointing in opposite directions. So they will form an angle of 180 degrees, or pi over 2. So we know that the cosine of pi over 2 is -1. So this integral becomes this. So this implies that the mass flow here at this phase 1 will be equal to this quantity, negative quantity, at the inlet. So now we carry out a mass balance at the outlet, which is at phase 2. And now the difference is that the angle between these two vectors is 0, because these two vectors are pointing out in the same direction. So we also express this surface integral at phase 2, and we obtain the following equation, and then the cosine of theta, which is 0, has to be equal to 1, positive 1, and then we obtain this quantity. And then our mass balance, which is this one, remember that we assume that the accumulation is equal to 0. That means that the density will not change with respect to time, so that term is equal to 0. And then we have the sum of the surface integrals across the two surfaces. So we have this integral, which has this result, plus this integral at phase 2. And then we obtain this relation. And then, yeah, we move this term to the other side. And then we obtain the following relation that tells us that the total mass is conserved. All the fluid mass that enters through phase 1 will exit through phase 2. So that's the meaning of the equation. That is the equation that was derived from here. So now let's just quickly assume that the fluid density is constant. I mean, the density is going to be the same one here as compared to here. So the densities can cancel each other, and then we have this relation that the product of the velocity at phase 1 multiplied by the surface at phase 1 has to be equal to the product of the velocity at phase 2 multiplied by the surface at phase 2, which means that the volumetric flow, because this quantity gives us volumetric flow, you remember this definition, is the same both at the inlet and at the outlet. So now let's assume that we have these changes in geometry. So the surface at the inlet is going to be much bigger compared to the surface at the phase 2. And we have two different values of velocity entering and at the outlet. So this equation, let's obtain an equation for U2. So U2, we pass this element to the left side of the equation, we obtain the following relation. And we know that this ratio is bigger than 1 because this surface is going to be bigger than this one. So this equation will tell us that the fluid at the outlet will speed up. The velocity is going to be much bigger. U2 is going to be much bigger compared to the velocity at the inlet. And what if we have the opposite case? That means that the surface, the area here, is going to be much bigger than the inlet. So that means that the surface is S2 is going to be bigger than S1. And then if we obtain the velocity at the outlet, we will obtain the following relation. And we know that S1 is smaller than S2. So that means that the velocity here, this velocity is going to be smaller than U1. So the fluid will slow down. You have probably encountered these behaviors in your daily lives. For instance, if you have a garden, you will use a hose to water the garden, and you will notice that the water comes out from the hose with a constant flow. But then if you put one of your fingers in the area from which the water comes out in the hose, you will notice that the fluid will speed up, and this is because you are decreasing the area of the hose. The same example can be seen in the sink from your toilet, from your bathroom. You have the faucet, and then you turn on the water using the control from your sink, and yeah, the water will come out from your faucet. But also, you place half your finger in the area from which water comes out in the faucet, you will also notice an increase in the velocity of the fluid. If you have some way of increasing the area of the faucet or from the hose, you will notice the opposite case, that the fluid will slow down because you are increasing the surface area from which water comes out. Yeah, those are just some typical examples, but also the continuity equation is very important in CFD because it allows us to simulate flows in complex geometries and also help us to satisfy different conditions. For instance, here we have a contraction geometry in which we have, this is an example of a planar 4-1 geometry, planar 4-1 channel geometry, which means that we have a big channel which has a height 4 times bigger compared to the height of this smaller channel. So we are pushing some fluid through this contraction, and then you will notice that this simulation that comes from a CFD, computational fluid dynamics simulation, you will notice that here we are decreasing the area because the height of the channel, of the small channel, is smaller compared to this huge surface area. And you notice that the velocity at the small channel is actually much bigger compared to the velocity here in the big channel. And this is because the continuity equation is being satisfied. Now let's we already obtained integral form of the mass balance, but we need a differential equation because it's much easier to work with differential equations than with integral equations. So to derive a differential equation for the mass conservation equation, we consider our mass balance, so we adopt this equation. The sign here is slightly different because it really depends on the notation. Here it is more convenient to use the sign. So if we use this negative sign, we will obtain a positive sign at the inlet, but a negative sign at the outlet. So it is really not much big of a difference. So you will see why this sign is convenient. So as we already know, this equation tells us that the change of mass with respect to time, that this is the accumulation term, has to be equal to the net mass flow across the surfaces of the control, of the volume control. So you can notice that these two equations are slightly different in the sense that we have here a volume integral, and here we have a surface integral. So we need to, in order to couple these two equations, we need that both terms are either both integrals are in surface integrals or in volume, or can be expressed as volume integrals. So the divergence theorem or the Gauss theorem let us transform a surface integral into a volume integral. So the quantity here at the middle is, if you remember, is mass flux. So this vector quantity can be expressed as this volume integral. So what is, so we go from a surface integral to a volume integral. So we obtain here the divergence of this vector quantity, which is the flux, the mass flux, this quantity, which has units of mass per square meters multiplied by second, by a unit of time. So what is the physical meaning of this equation? Well, this equation, here we have flux, mass flux, in a point of a volume control. So the divergence theorem, the divergence of this vector quantity, gives us the total mass of the fluid on a point. And if we sum the total mass, the mass flow in all points of the volume control, this quantity gives us the total mass in the volume. So this total mass in the volume is going to be equal to the flux of the mass across the surfaces of the control volume, of the volume control. So that's basically the physical meaning of the divergence theory, that we have a flux of mass on a point. The divergence give us the flow of mass in a point if we sum all the mass in all the points of the volume control has to be equal to the mass across the surfaces of the volume control. And then, yeah, we have this expression. So this surface integral can be expressed as this. And then, yeah, we obtain now the both integrals are expressed as volume integrals. So if we know that the volume and the time are independent variables, we can introduce the derivative with respect to time inside the integral, and we obtain this equation. And then we can introduce both terms into the same integral, and we obtain the following relation. And then, since the volume cannot be zero, that means that this volume has to be finite. It cannot be zero because otherwise it will be nothing. So the only way that this equation, this integral, can be satisfied is if the integrand is zero. That means this quantity inside the integral is the only way that this quantity has to be 0 in order to satisfy the whole integral. Therefore, we obtain this differential equation, which tells us that the mass is conserved in each point in space. The first term corresponds to the accumulation of mass, while the second term is associated with the mass that enters or exits a volume control. So the continuity equation in Cartesian coordinates, that means that, for instance, the velocity field is expressed as follows. So we have a velocity in x direction, a velocity in y direction, and a velocity in z direction. And then this equation can be expressed as this one. So this is an scalar equation. So we have changes of the density with respect to time, but we also have changes of mass, because remember, velocity of the fluid multiplied by the density give us the mass flow. That gives us the mass flux, sorry. How does the mass changes in x direction, how does the mass changes in y direction, and how does the mass changes in z direction. We can simplify this equation further. If the density of the fluid is independent on position and time, then the continuity equation for an incompressible fluid, that means a liquid, that means where we do not observe changes in density, then this equation is reduced as follows. So we can leave. The density can be is not considered here because it doesn't really affect the mass of the mass balance. The density is not relevant for incompressible fluids or liquids. And then this equation can be expressed as follows. And this is an interesting relation because let's say you have somehow you obtain the velocity field of a fluid. You don't know if it's either a gas or a liquid. But if you obtain this expression, this relation for the fluid velocity, and if that relation is equal to 0, that means that you have a liquid. If this expression is different than 0, that means that the fluid will be a gas. So with this information we conclude the first part of the video. In the next video we will talk about the Newton's second law and the mass and the momentum conservation equation. So thank you for staying here. Thank you for watching the video. So see you in the next one.